Welcome back to another video. Here, we will talk about joint probability distributions. Informally, a random variable X represents possible outcomes of an event. Random variables can be categorized to discrete and continuous variables. Discrete variable only accepts a finite set of possible outcomes, whereas continuous variable accept an infinite set of possible outcomes. For instance, discrete random variables X can accept values 0 and 1 to represent outcomes of a coin toss, either heads or tails. Or discrete random variable Y accepts values 1 to 6 to represent the outcome of rolling a six-sided die. As for continuous random variables, X can accept any value in real numbers to represent the heights of students in a B2100, which can vary continuously. Or Y can accept values in real numbers to represent the time taken to reach your hall from the department, which is also a continuous value. For discrete random variables, also known as PMF, a probability mass function is used to define the probability of the random variable X taking on specific values. Since a probability mass function represents probabilities, it must follow these rules. Probabilities must be non-negative, meaning they cannot be less than 0. Probabilities cannot be greater than 1. The sum of all probabilities for every possible value that the random variable X can take must be equal to 1. For continuous random variables, the set of possible outcomes forms a continuous range, such as all real numbers within an interval. Because there are infinitely many values in such a range, the probability of X being exactly equal to a single, specific point is 0. Instead of assigning probabilities to individual values, we use a probability density function, also known as PDF. A probability density function gives the probability over an interval of values rather than an exact value. To calculate the probability that a continuous random variable falls within a range, such as between A and B, we use the integral of the probability density function over that range. This integral represents the area under the curve of the probability density function within the specified interval. Properties of a probability density function. The probability density function must always be non-negative because probabilities cannot be negative. The height of the probability density function can be greater than 1, since the function itself does not directly represent probability. Instead, the area under the curve over an interval gives a probability. The total area under the probability density function across the entire domain of the random variable must be equal to 1 to account for the entire probability distribution correctly. Let's explore an example of a probability mass function and a cumulative distribution function using the scenario of rolling a fair die. Consider a discrete random variable, X, that represents the outcome of rolling a fair six-sided die. The values that X can take are 1, 2, 3, 4, 5, and 6, which correspond to the 6 faces of the die. Since the die is fair, each outcome has an equal probability of occurring. The probability mass function assigns a probability of 1/6 to each of these values because there are 6 equally likely outcomes. The cumulative distribution function, or CDF, describes the probability that the random variable X is less than or equal to a certain value. To calculate the cumulative distribution function, we add up the probabilities for all values that X can take up to the value we are interested in. For our die example, the probability of X being less than or equal to 1 is 1/6. The probability of X being less than or equal to 2 is the sum of the probability of X being 1 and the probability of X being 2. This equals 2/6. The probability of X being less than or equal to 3 is the sum of the probability of X being 3 and the probability of X being less than or equal to 2. This equals 1/2. We can continue in the same way to find the cumulative probabilities for 4, 5, and 6. The probability function associated with a continuous random variable is a continuous function that integrates to 1 over its entire domain. For example, consider the negative exponential function. Since this is a continuous distribution, we know that the integral of its probability density function over its domain must equal 1, as demonstrated here. To find the probability of the random variable falling within a specific interval, we need to integrate the probability density function over that interval. For instance, if we want to calculate the probability that the random variable X lies between 1 and 2, we should compute the integral of e to the power of negative x from 1 to 2, which equals approximately 0.23. The joint probability distribution describes the likelihood or probability of two random variables, x and y, occurring together or coexisting at the same time. In other words, it gives the probability that x takes a specific value and y takes another specific value simultaneously. For example, if you roll two dice, one representing x, the outcome of the first die, and the other representing y, the outcome of the second die, the joint probability distribution would tell you the probability of both dice showing certain values at the same time, like x equaling 3 and y equaling 5. The sum of all possible joint probabilities in a joint distribution equals 1, as it encompasses all possible combinations of x and y in both discrete and continuous cases. When you toss two dice, you're dealing with a joint random variable that is determined by the outcomes, or faces, of both dice. Each die has 6 faces, numbered from 1 to 6. So, when you toss two dice, the result of the toss is a pair of numbers, one representing the outcome of the first die, die 1, and the other representing the outcome of the second die, die 2. Since each die has 6 faces, the total number of possible outcomes when tossing two dice is the product of the number of faces on each die. That is 6 times 6 is equal to 36. Hence, there are 36 possible outcomes when tossing two dice. As for an example for the continuous case, we can look into the joint distribution of people's height and weight. We want to understand the joint probability distribution of two continuous random variables, height, x, and weight, y, of adults in a population. Since both height and weight are continuous variables, they can be described using a joint probability density function, specifically a continuous normal distribution. The joint probability density function describes the likelihood of different combinations of height, x, and weight, y, occurring together. In this case, we assume that both variables follow a bivariate normal distribution, which is a type of continuous probability distribution for two variables that are normally distributed. Key components include: mu of x is the mean of the height distribution, average height in the population. Mu of y is the mean of the weight distribution, average weight in the population. These are the central values for each of the variables, height and weight. Sigma of x is the standard deviation of the height distribution, which measures how spread out the heights are from the mean. Sigma of y is the standard deviation of the weight distribution, which measures how spread out the weights are from the mean. These tell us how much variability or dispersion exists in the height and weight values in the population. Rho is the correlation coefficient between height and weight. This measures the strength and direction of the linear relationship between height and weight. Thank you for listening to this short lecture on Introduction to Joint Probability Distributions.